So reminders that we have an assignment that's been pushed back to tomorrow, get that in by tomorrow night. I'll also have an exam study guide out to you by end of day tomorrow. Because we have an exam a week from tomorrow. I think that's just about everything that's important to schedule for now. Anyone else have any questions about schedule, due dates? My goal is to get a project to you by early to mid next week so that you have a second option for your project. Again, if that does not align with your workload at the end of a quarter, I highly recommend getting started on the CYK project. All right, we ended last class talking about computability and decidability, giving definitions for computable and decidable. Again, computable was that we could construct a Turing machine that, given the domain of F, gives some kind of domain or gives some kind of range for that, if we can compute the value of a function. So we can figure out what value is associated with every element of its domain, then it is computable. If there is any element of its domain that is not, we can't figure out the associated value in the range, then it's not computable. We also said that it is decidable, so language is decidable if we have a yes/no question. And if a Turing machine exists, it can always answer yes or no for every possible instance of that problem in the domain of that problem, then it is decidable. So for instance, whenever you have a yes/no question, like membership, that is a decidability question. Since the answer is either yes, the string is in the language, or no, the string is not in the language. So a recursive language is decidable. A recursively enumerable language is not decidable, at least in terms of the membership question. Your question?
Oh, I was just like, with decidable, is that just limited to yes or no, or is that any one that has like a finite set of?
It is
possible answers?
limited to yes or no for now. If it has a limited number, then there would be a function that works, so then it would be computable. So decidable is just the binary version of computable. One thing to note, and it's kind of interesting, is there are problems that are decidable on a particular domain and not decidable on another domain. So it is a domain-specific question that you ask. You can't ask, is this language decidable? You have to say, is the membership of this language decidable? Because that immediately tells you the domain, which is all of the possible input strings in the language. So we need something that restricts the domain to one possible domain. All right, where are my grad students? They're the ones who would appreciate this. We're gonna go into the halting problem, and the halting problem is one of the fundamental Turing machine arguments that we make that has a really interesting result. So the halting problem says we want to write a Turing machine that's going to figure out if given as input another Turing machine and a string, if that Turing machine applied to that string will halt or not halt. So think of it as you're writing a program that takes as input an arbitrary program with an arbitrary input to that program. You want to analyze the input program and figure out if on the input to that program will go into an infinite loop. So you're creating we're going to create a large scale program. Think of it as a very big box. We need to write this program. And this program will take as input some other program. And it will take some input to that program. And the goal is to spit out either, yes, this program applied, or this string applied to this program. Goes into an infinite loop, or it does not. The program that we write has to be generic enough to work for any program and any input to that program. So the same logic that we write here has to be true, has to work, no matter what program and what string we use. So the question that I ask is, what is this program? How would you even start trying to write a program that does this? Yeah?
Not writing it, but we have to first figure out if it's like, is it recursive? Because like recursive allows for something to be in a language and not in a language. I guess, right? Or is that,
It emulates a loop. So we would have to look for infinite recursion because that's a form of an infinite loop. So we'd have to be able to identify that. We'd have to be able to identify any kind of an infinite loop. How many kinds of infinite loops are there? It's pretty much infinite. There are so many ways that you can write logic that does not terminate, that we need some way of making sure that this works. So the question I'll ask is, can we do it? Yeah, that's the right answer. Oh no, now we don't even have the little thing to erase. This is bad. Okay, so this turns out to be impossible. No such program exists. It's not that no such program has been discovered, but it is impossible to construct such a program. How do we know that it's impossible to construct such a program? If we were to use something like a direct proof, we would have to iterate over all infinite possible programs and show that those programs don't solve this problem, which would never terminate. So we need some kind of logical argument, some kind of proof-based argument that doesn't iterate over every possible program and asks, does this program solve the halting problem? So we're going to proceed to the proof by contradiction. This is usually the form that you will use. You basically are going to assume that such a program exists and then logically derive some kind of contradiction. So we're going to assume that such a Turing machine exists that solves the halting problem. We're going to use H. The Turing machine, instead of being called M or some arbitrary kind of M, we're just going to call it H. Capital H is the Turing machine that solves the halting problem. It will end in a final state called Q sub Y if the program that is fed to it, M, accepts the string that was fed to it, W. And it will also halt in a final state Q sub N if M does not accept W. And we just look at which state we ended in. And if we ended in Q sub Y, then this M on W halts, and Q sub N is M on W does not halt and goes into an infinite loop. But at least then we would have identified that it goes into an infinite loop, so we can halt and not go into an infinite loop. Does that make sense? So if we wanted to kind of visualize this, this is using slightly different terminology because the book uses more out there terminology. But as input, we have the machine and the string. We start in some initial state, and via some logic, we either end up in Q sub Y or Q sub N, depending on whether M on W goes into an infinite loop or does not. So that's our setup. We then need to start modifying this machine because we want to derive some kind of contradiction. So the way that we would want to proceed with this is we basically want to say that we're going to make modifications to this halting machine problem that solves this problem such that it both solves the problem and doesn't solve the problem, or neither solves the problem nor doesn't solve the problem, both of which are logical contradictions. Right? That can't happen. But if we can make changes to this machine that we're stating exists in a way that causes it to both answer the question and not answer the question, then the machine itself can't exist. So the change we're gonna make to the halting machine, Turing machine H, the one that starts in an initial state and goes to either Q sub Y or Q sub N, we're gonna make a small modification and call the resulting Turing machine H sub loop. And we call it H sub loop because if we reach Q sub Y that tells us that M on W enters an infinite loop, rather than halt, we're going to ourselves enter an infinite loop. So basically we do this. Rather than halt from Q sub Y, making it a final state, we're just going to immediately transition into an infinite loop. Why? Because we can. So this is the diagram for H sub loop. Just keep that in the back of your mind. It's exactly the same. It takes M and W, this arbitrary Turing machine, an arbitrary string that when you run M on W, either halts or doesn't halt. If it halts, we go into an infinite loop. If it doesn't halt, then we still are able to identify that it does not halt by finishing in Q sub N. We need a third Turing machine that is going to be H sub proof. It's still related to the halting problem, so we're still going to call it H. So now we have M, the input. We have H, the Turing machine that solves the halting problem. We have H sub loop, a modification of the Turing machine that solves the halting problem that goes into an infinite loop if we identify that M on W halts. H sub proof is going to take as input the binary encoding of M, the machine that we fed to H. And it's going to copy it, so it appears twice. Once it does that copying process, it's going to go back to the beginning, and instead of ending in a final state and halting, it's going to end in its initial state, where it was ready to process this before. After it finishes this, it behaves exactly like H sub loop. So it's going to read M and read W and either halt or not halt. We're going to encode the entirety of H sub proof as a binary string that we're going to call W sub proof. This is the string that has H sub proof on it. We're going to make a substitution. The machine that we originally fed H, M, we're going to substitute now for H sub proof. And give it as input itself, W sub proof. So we're giving H sub proof as a string its own representation. Its own binary representation. And then if we run H sub proof on its own W sub proof, we see that if H sub proof halts on W sub proof, that means that H sub proof did not halt on W sub proof. And if H sub proof does not halt on W sub proof, that only can happen if H sub proof halts on W sub proof. This is a logical contradiction. This cannot possibly happen. This is a lot, so I have a video to give you a little bit more of a visual for this, because this is not particularly easy to see. Yay, it's video day. So this entire video is really interesting. It's incredible to watch. It's basically about the flaws of mathematics what we can and cannot state in the same way that we have kind of been talking about the theory of computation. What can we and can we not compute? What can and can't math recognize or resemble or write down? And you find that math has some pretty fundamental flaws associated with it. And one of them is this halting problem. Now, the real question is, do we get sound? I think we do, and it just wasn't on.
First and final big question from Homer.
So I guess the first thing I should say is the beginning of this. I don't know if people know Veritasium. Veritasium is a phenomenal YouTuber who does lots of math related stuff, but we find that math is not complete. We have no way of showing whether or not math is consistent. And the last thing is math decidable? And we will use the exact same Turing machine halting problem to show that math is not decidable, which is intriguing. So we will, let's start here.
Is mathematics decidable? That is there an algorithm that can almost determine whether a statement follows from the axioms? And in 1936, Alan Turing found a way to settle this question. But to do it, he had to invent the modern computer. In his time, computers weren't machines, they were people, often women who carried out long and tedious calculations. Turing imagined an entirely mechanical computer. He wanted it to be powerful enough to perform any computation imaginable, but simple enough that you could reason through its operation. So he came up with a machine that takes as input an infinitely long chain of square cells, each containing a 0 or a 1. The machine has a read-write head that can read one digit at a time, and then it can perform one of only a few tasks: overwrite a new value, move left, move right, or simply halt. Halting means the program has run to completion. And the program consists of a set of internal instructions. You can think of it like a flowchart that tells the machine what to do based on the digit it reads and its internal state. You can imagine exporting these instructions to any other Turing machine, which would then perform in exactly the same way as the first. Although this sounds simple, a Turing machine's arbitrarily large memory and program mean it can execute any computable algorithm if given enough time. From addition and subtraction to the entire YouTube algorithm. It can do anything a modern computer can. That's what made the Turing machine so useful in answering Hilbert's question on decidability. When a Turing machine halts, the program has finished running and the tape is the output. But sometimes a Turing machine never halts. Maybe it gets stuck in an infinite loop. Is it possible to tell beforehand if a program will halt or not on a particular input? Turing realized this halting problem was very similar to the decidability problem. If you could find a way to figure out if a Turing machine would halt, then it would also be possible to decide if a statement followed from the axioms. For example, you could solve the twin prime conjecture by writing a Turing machine program that starts with the axioms and constructs all theorems that can be produced in one step using the rules of inference.
This was explained earlier in the video, but the twin primes conjecture is the idea that there never stops being two primes that are just two away from each other. Regardless of how far you go in the positive integers, you will eventually continue to see another two consecutive odd numbers that are both primes.
Then it constructs all theorems that can be produced in one step from those, and so on. Each time it generates a new theorem, it checks if it's the twin prime conjecture. And if it is, it halts. If not, it never halts. So if you could solve the halting problem, you could solve the twin prime conjecture and all sorts of other unsolved questions. So Turing said, let's assume we can make a machine H that can determine whether any Turing machine will halt or not on a particular input. You insert the program and its input, and H simulates what will happen, printing out either halts or never halts. For now, we don't worry about how H works. We just know that it always works. It always gives you the right answer. Now, we can modify the H machine by adding additional components. One, if it receives the output false, immediately goes into an infinite loop. Another, if it receives never halts, then it immediately halts. We can call this entire new machine H plus, and we can export the program for that entire machine. Now, what happens if we give this machine its own code, both as program and input? Well, now H is simulating what H plus would do given its own input. Essentially, H has to determine the behavior of a machine that it itself is a part of in this exact circumstance. If H concludes that H plus never halts, well, this makes H plus immediately halt. If H thinks H plus will halt, then that necessarily forces H plus to loop. Whatever output the halting machine H gives, it turns out to be wrong. There's a contradiction. The only explanation can be that a machine like H can't exist. There's no way to tell in general if a Turing machine will halt or not on a given input. And this means mathematics is undecidable. There is no algorithm that can always determine whether a statement is derivable from the axioms. So something like the twin prime conjecture might be unsolvable. We might never know whether there are infinite twin primes or not. The problem of undecidability even crops up in physical systems. In quantum mechanics, one of the most important properties of a many-body system is the difference in energy between its ground state and its first excited state. This is known as the spectral band. Some systems
Probably all that we need to see. The rest of this video is just as cool as that, but I'll leave that to do on your own time. Highly worth it, just to see the kinds of theoretical things that we can show that then have real practical applications, like we may never be able to show or prove the twin primes conjecture. We may never be able to determine whether or not pi halts or repeats. It may be impossible to be able to do these things or ever derive an algorithm that can give us an answer, which is intriguing. So hopefully that was a little bit revealing as to how the halting problem works and what that, what do I want to call it, what this contradiction actually means. Anyone have any questions on the halting problem or how we derive that contradiction or what that contradiction means? No such machine exists that can tell us whether or not a machine is going to halt on a particular problem, at least a generic one. You could write a program for a specific other program that could determine whether or not it could halt. You just have to analyze it line by line or be able to, the behavior, so you can give this input the specific behavior that you expect. And then you can determine something like, theoretically, this program will always halt within the first 1,000 steps if it's going to halt. So if it runs 1,001 steps, it will not halt. But you can make no such general claims about an arbitrary algorithm. There are algorithms out there that take longer than 1,000 steps to halt, that take longer than 1,000,000 steps to halt, take longer than a quintillion steps to halt. There's no arbitrary endpoint. One other interesting conclusion we see from this is that if the halting problem were decidable, meaning that we could determine yes or no, then every recursively enumerable language would also be recursive. And we have also shown that there exist recursively enumerable languages that are not recursive. So this leads us, knowing about the halting problem, to what kinds of arguments can we make about other theoretical arguments in computer science. If we had a way of saying, I can algorithmically convert the halting problem into another problem, we know that that problem is also not decidable. Because if that problem were decidable, we could flip the algorithm and convert this problem into the halting problem, and then the halting problem would be decidable. So we can use this undecidable problem as a way of showing that other problems are also undecidable. It's very similar if you've seen NP completeness in any of your prior classes, the way that you can use a reduction. Given that you have an NP complete algorithm, you can derive more NP complete algorithms by finding polynomial time reductions into the other problems. If you could solve the other problem, you'd have a polynomial time algorithm that would convert it to solve another NP complete algorithm, and then all NP complete algorithms would be solvable in polynomial time. It's a whole class of algorithm that we don't know if it's solvable in polynomial time or not. But if one of them is, then all of them are, which is kind of scary. So a reduction is the same between all of these domains. It's just a logical connection from one problem to another problem. A way of saying if we had a solution to one of these problems, we'd be able to solve this other problem. And if we can say for any one of these problems, we can't solve this problem, then we can perforate that throughout the rest of this logical argument to say the rest of these problems are also unsolvable. Or at least in this case, undecidable. So this just states that again. One thing to note here, this last bullet point is very useful as we figure out more and more undecidable problems. Note that you don't have to tie all of them back to the halting problem. You can tie any of them to each other. And that way you kind of come up with a graph or a web of different problems and their associated relations based on proofs that have been shown. I'm not going to ask anybody in this class to do undecidability proofs or reductions, but it's very important to know that this is the kind of proof that you use to show something like a problem is undecidable or a problem is not solvable. We can't reason through logic to be able to decide this particular problem. So I'll give you an example reduction because I think it's useful to see what these look like. Let's say that the query problem that we want to figure out is given a Turing machine and a string. We want to figure out whether that Turing machine ever enters some particular internal state of its. I give you an example like Q3. Given this input, do we ever enter Q3? First of all, do we think that this problem is decidable? It's a yes or no question, right? It either enters Q3 or it does not enter Q3. I see some people saying it's undecidable. What logically or intuitively tells you that this might not be decidable? Yeah,
Just because we say some state Q3, we don't know what Q0, Q1, Q2 are. That's like where I first go towards.
okay, sure.
What entails Q1, Q2, Q3, we can say a we can say a Q3, but is there anything that like gets to Q3 in a way?
Yeah, we know if it enters Q3, then it enters Q3. Once it gets there, we know that it can get there. But if it has not yet reached Q3 at some point in its derivation, is it never going to reach Q3? Will it eventually reach Q3? We don't know yet. And we don't know until it halts, right? When it halts, for sure, and it didn't enter Q3, we can answer no. But what if it never halts? What if it goes into an infinite loop? If we could identify whether or not it goes into state Q3 or not, then we would have a way of answering the halting problem intuitively, right? We would have a way of saying we could map these problems onto each other and say these are very similar. So we just have to find a way of converting one problem into the other problem. And if we can do so, we can show that they have the same level of decidability. If one is decidable, then the other is. If one is undecidable, then the other is. And we know the halting problem now is undecidable. So if we can map these two problems onto each other, then this problem will also be undecidable. So how do we reduce it to the halting problem? We assume there exists an algorithm that solves this problem. This problem is called the state entry problem. Again, we'll use a proof by contradiction, except that the end of the proof by contradiction will no longer be straight up a logical contradiction. It will be basically that if this is decidable, then the halting problem is decidable. Since we know the halting problem is not decidable, this will also not be decidable. Just like before, we will modify the input m to get m subproof from the halting problem in such a way that m subproof halts in this query state, because remember this is a state entry problem. We're going to say that Q is the state. If we enter state Q, we want to accept. If we do not enter state Q, then we reject. So m subproof halts in this query state Q if and only if m halts. Then you apply this algorithm to this Turing machine m subproof on W with the query state Q that was already this Q from step 2. The conclusion from this is if m subproof answers that we enter state Q, then m subproof halts. If m subproof answers no, state Q is not entered, then m subproof does not halt. Look at that, we solved the halting problem. We came up with an algorithm that was capable of determining whether or not this machine halts by determining whether or not it enters Q or not. So if the state entry problem were decidable, we could solve the halting problem. Since we know we can't solve the halting problem, the only assumption that we made was that the state entry problem was decidable. We had this algorithm A that solved it. Since that was the only logical assumption that we made, it must be incorrect that such an algorithm exists. Does that process make sense? You're able to follow through that kind of logic of how you can set up and emulate Turing machines on other Turing machines to be able to solve an unsolvable problem. That creates our contradiction. I solved an unsolvable problem. This creates, I don't know if this was discussed at all in discrete math, but I find that this is truly interesting in another abstract way. Think about how easy it is to perforate misinformation through something like social media. Think about how easy it is to add a single false piece of information to your own personal knowledge base. You just have to take somebody at their word who is not being 100% truthful. As soon as you add a single piece of misinformation into your knowledge base, you can use 100% perfect logic to derive an infinite number of false statements. You can basically make almost anything true logically starting from this falsehood. You make this assumption that an algorithm A exists for the state entry problem, you can solve the halting problem. So this just shows how important it is to fact check and know everything that you think that you know, because you can use perfect logic to derive any number of false statements if you're not sure whether or not something is true or not, or you're taking somebody else at their word. It'd be very interesting and revealing for, I think, each of us to go through everything that we think we know and identify everything that is actually false. And then it makes you wonder, as you start to think about this, how do I know that anything that I think is true is actually true? They're all based on assumptions that eventually somebody told us, or that we derived for ourselves based on something that somebody told us. This is why the scientific method is so important, is it allows us to go back to the roots and prove something from scratch to be able to show that this particular kind of thing is true. And I think that's partially responsible for how easy it has become to believe misinformation in our society. So I find that to be really interesting. So next, we're going to talk about undecidability in recursively enumerable languages, because as we know, recursively enumerable languages, if they're not recursive, aren't decidable. We can never answer no, a string is not in the language of a recursively enumerable language. That may cause something like an infinite loop in the grammar. Or in some kind of state machine. So we know there's no membership algorithm. We can't determine yes or no, a string is in or not in a recursively enumerable language. We can eventually determine yes, but no can be a very difficult problem. So there's not much that we can do with recursively enumerable languages. There's just straight up not much we can do. They're an interesting class of language of which we can't do a lot of reasoning about. Most simple questions we can ask about recursively enumerable languages, not decidable. Some examples of this. We have an unrestricted grammar. And again, we showed before, and the textbook has the proof that an unrestricted grammar is equivalent to a recursively enumerable language. Here's a simple question. Is the language described by the grammar empty? Are there no strings that are in that language? This is undecidable. That kind of seems strange, right? We think it'd be really easy to determine if there's a single string that is in this language. But if you had been working on this problem for 1,000 years and hadn't yet discovered any strings that are in the language, could you write a program that would say for sure, no, I've been processing this for this long, nothing's in the language? You could write a grammar that would take longer than that to find the first string that's in the language. Therefore, no matter what the arbitrary endpoint is for your algorithm, there would exist some counterexample where you could find a non-empty grammar that looks empty to that point. So proof for this is just a reduction to the membership problem. Assume we have some Turing machine. Is the language accepted by that Turing machine finite? Decidable or undecidable? What do we think? Who thinks it's decidable? Who thinks it's undecidable? For those who say it's undecidable, what makes you say that? Yeah.
You won't know until you know.
Yeah, it's kind of the same kind of logic that we've been saying. We can say yes, if we're going through an enumeration procedure and eventually we stop enumerating strings, it's like, all right, the algorithm finished, it halted, then it's finite. But if it's still generating output, who knows if it's going to stop eventually or not stop eventually? There's no way we can tell the no answer from this. So the finiteness of a given Turing machine is undecidable, which is intriguing. This proof is a reduction to the halting problem. If we could solve whether or not a language accepted by a Turing machine is finite, then we could solve the halting problem. Assume we have a Turing machine over a small input alphabet, AB. Are there two strings in the language that are accepted by the machine that have the same length? What do we think? Decidable or undecidable? Some people saying decidable, some people saying undecidable. The answer is this is also undecidable. If you generate two strings that are of the same length, great, you halt. If you have not yet generated two strings that are of the same length, are you eventually going to generate another one that is the same length? We don't know. Maybe for a particular grammar, we could say something like, all right, if we go through this grammar, we can see that every string that is generated, the more productions we apply, the longer the associated string is going to be. But there are grammars that don't abide by that. So we would never know if we just go through more. Are we eventually going to reach a point where we shorten it up and can produce something that's the same length as something else? No matter how long we spin our wheels, I could derive a grammar that would be a counterexample to that. So everything here is undecidable, And these are even simple questions, right? These seem like they would be really simple to write an algorithm for to be able to determine. And they might just spin forever, which is intriguing, but it also means that we can't say very much about recursively enumerable languages. So very interesting class of language that we don't study very much because we can't answer most simple questions about it. So the halting problem is kind of cumbersome to work with. The reductions that actually lead back to the halting problem often involve lots of steps and lots of logic. So something that you can do if that becomes a problem is to derive something from the halting problem that is closer in terms of a proof, fewer steps to many of the interesting problems that we want. So there is one very particular algorithm that is used for many reductions that would go to the halting problem that instead go to this problem as a proof, and it makes the proof a lot easier to end in this particular state. So we can come up with some better, easier middle ground problems, and this is called the post-correspondence problem. So as input, we're given two sequences of the same length, n strings, over some possible input alphabet. And PC for this is going to stand for post-correspondence, not politically correct. There is a post-correspondence solution if there is an arrangement of each set of strings that produce the same output string. So let's give you an example. We have, let's actually zoom in on this so you can see it a little bit better. We have strings 1, 1, 1, 0, 0, and 1, 1, 1 as the W sequence of strings. And then we have a V sequence of strings that we will call 1, 1, 1, 0, 0, 1, and 1, 1. Can we arrange these in some fashion such that they produce the same output? And sure enough, we can. If we do W1, W2, W3, and V1, V2, V3 in that order, you end up with the same output string. Does that make sense? What do we think? Decidable or undecidable? Yeah,
I had a question.
Yeah.
I don't know the definition of post correspondence. Do I need to know that?
No. It's just, this is basically the name of this particular problem.
Okay.
So it's mapped the name to the idea. And I'm not gonna quiz you or test you on the name post correspondence problem, so you don't need to remember it, just for the sake of giving it its official name. That's the official name.
Okay.
So it seems like it should be decidable. You just iterate every possible pairing of this and every possible arrangement. But there are sequences of strings that have odd loops in them that mean that there's actually no way that you'd be able to answer this problem for it. So it's undecidable for certain strings. There's a modification to this problem where we have two initial strings that we will call W1 and V1 that must start the problem. So instead of saying you can arrange any of these in any order, we know that W1 must start this, and then after that, we have any arrangement. We have V1 that's guaranteed to start this, and then we can have any order of the remaining V's. So we kind of lock W1 and V1 in place. This will map to grammars with start states where we know that the start symbol is what starts any derivation of that grammar. So we can show that the post correspondence problem maps onto grammar derivations, which is really interesting and allows us to be able to say things about grammars that we wouldn't otherwise be able to say. So we can use reductions from the post correspondence problem to make claims and proofs about context-free languages. And context-free languages are the main syntax of compilers. They're the syntax checkers of compilers. So we can determine what is possible and not possible for a compiler to do based off of reductions to and from the post correspondence problem. One outcome from this is, we stated this before, there is no algorithm for deciding whether or not a context-free grammar is ambiguous. I made that claim earlier, but now we know how we can prove it. We tie this back to the post correspondence problem, which ties back to the halting problem. And it turns out that the halting problem and the generation of the halting problem is the entire reason we have a proof for the reason why the ambiguity of context-free grammars is undecidable. There also exists no algorithm for deciding whether the intersection of languages defined by two arbitrary context-free grammars is the empty set. So you take everything that's shared in common between two languages, and you find that there's nothing in common. That is undecidable. That's another reduction from the post correspondence problem. Other proofs that you can come up with, if we have two grammars, G1 and G2, do they generate the same language? Turns out that is undecidable. If we have two context-free grammars, is one grammar a subset? Is the language generated by that grammar a subset of the language generated by the other grammar? That is also undecidable. If a grammar is a context-free grammar, is the language of that grammar regular? That is undecidable. And if we have two grammars, the first one is context-free and the second is regular, is the regular grammar a subset of the context-free grammar? That is undecidable. Finally, if we have, again, a context-free grammar and a regular grammar, is the intersection of the context-free grammar and the regular grammar the empty set? That is undecidable. So we have answers to all of this because of the post correspondence problem. They all link back to the post correspondence problem. And they're easier proofs with the post correspondence problem than they are with the halting problem. You could use either, but the choice of the algorithm or the problem that you choose to reduce to will determine how difficult that proof is. Some of them will be easier, some of them will be more difficult. The last thing I want to talk about today, and it's the last thing before we dive into compilers, we're finally hitting compilers tomorrow, is about the efficiency of Turing machines. In terms of how useful is this material, we know that as computer scientists, we care a lot about efficiency. And we've been asking a lot of theoretical questions about just, is something possible and not is something efficient? All exponential time algorithms are possible. All factorial time algorithms are possible, but they aren't efficient or practical. There are different constructions within Turing machines that have vastly different complexities. Think of this like you and your neighbor are answering the same problem. Maybe you're implementing, I would just say, sort the following array of numbers. And we know that even the same sorting algorithm can have different complexities on different inputs, or the way that you solve a particular problem, you might apply two different algorithms that solve the same problem, but the way that you do it have vastly different complexities. If one person solves it using quicksort and one person solves it using bubble sort, then one algorithm is just strictly better than the other, even though they solve the same problem and do the same thing. In terms of looking at the inputs and outputs, the actual process varies in complexity. We'll actually have to hit this tomorrow, I think. There's just enough here that it's going to take a couple minutes to go over. So we will very briefly talk about this and then transition to compilers tomorrow.
Not sure if it starts.